Thank you. Yes, this talk has changed. If you're looking for my talk about the GIL, this isn't it. This is a talk about removing Python's GIL. And thank you all for practicing getting in your planes for later tonight. As a preface for this talk, I want to warn you, this talk is going to be exceedingly technical. I was encouraged to make this talk very technical, actually, by the program committee. I'm going to talk about a lot of technical topics, and I don't really have that much time to introduce them. I'm assuming that you're pretty familiar or comfortable, at least, with me talking about multithreading and about CPython internals from a very high level. I'm not going to be digging way down, but you have to understand kind of the basics of CPython internals, like reference counting. If you're not familiar with that stuff, a good refresher course or an introduction would be my previous talk called Python's Infamous GIL, which again, I was supposed to give here, but then we switched it. There's videos of that online. So let's start with a little history about the GIL. The GIL was added in 1992. Guido wanted to add support for this new thing that operating systems are starting to do called threading. And he needed a way of protecting the global and static variables inside of CPython so that you couldn't have races between multiple threads. And so he added this thing called the GIL 24 years ago. And let's make no mistake, this was a lovely design and it has served us very well. That has a lot of wonderful positive attributes. I'm not in the camp of GIL haters. I think I think people who are GIL haters are kind of misinformed. So let's talk about the ramifications of this design. First of all, the GIL was incredibly simple, which meant it was easy to get right, both for us and it was easy for CPython C extension authors to get right. It had no deadlocks because there's only one lock, so you can't have deadlocks between two locks because there aren't two locks. It had very little overhead. You touch the GIL infrequently. And if you had single-threaded code, it ran incredibly fast because, again, we didn't have any synchronization overhead. We didn't have any locking and unlocking. Your code just ran, almost no overhead, and it ensured that it sort of paved the way for your code to run very, very quickly. If your program is I/O bound and you use multiple threads, then everything worked great. And this is actually the original use case of threading because computers didn't develop multiple cores until very recently, or at least consumer level hardware. The problem is, of course, if you run multiple threads and your program is CPU bound, you're kind of out of luck. The GIL ensures that your code is only going to run on a single core at a time, which was fine in 1992. It was rare that you would see a multi-core computer back then, but the world has changed around us over the subsequent 24 years. So these days, our wonderfully thin and light laptops and our phones and our watches and our eyeglasses have all gone multi-core. We live in a deeply multi-core world, and Python is still doing single core. I have a workstation at home that has 28 cores in it. Like, I want multi-core stuff. But Python just isn't ready for it. This is a comment actually sitting in the Python source code right now. My suggestion is that it's time to consider moving beyond rudimentary thread support. After all, your computer has all these wonderful resources, and Python is able to take advantage of all of them, except for the multiple cores. And this is kind of a sore point. A lot of people, yeah, if you have a problem, you can go multi-process, then of course, yes, you can take advantage of the multiple cores. But there are definitely problem domains where that's not true. And those people would maybe love to use Python, and they just kind of can't. Now, there was an attempt to remove the GIL before. And when I say attempt, what I mean is they successfully removed the GIL. This was back in Python 1.4 days in 1999. It was literally like December of 1999 the patch was posted. So right before the Y2K bug and everyone was nervous. This change did not require changing the C API, so your code usually would still just run. It took all of those global variables that were in the Python core that Guido was protecting with the GIL and moved them into a single struct called pythreadstate, which we actually, that got merged. We have that today. It added a single mutex lock around anchor and decker. On Windows, it used something smarter called interlocked increment. And it made your code between 4 and 7 times slower. So again, I want to just make this point. The GIL makes your code run fast, and removing the GIL makes your code run more slowly, and that's the challenge of removing the GIL. So if you want to know more about this free threading patch, David Beasley wrote a wonderful blog post called An Inside Look at the GIL Removal Patch of Lore. Very easy to find on the internet. I've referred to it a lot. But even that is 15 years ago. I feel like it's time to try again, so I have this project I'm calling the Gilectomy. That's the surgical removal of the GIL. And I've thought about the problem a lot. So I would say that there are 4 technical considerations you must take into account when you try to remove the GIL. Those are reference counting, of course. Python objects are reference counted in order to keep track of their lifetimes. Very quickly, if every Python object has a number associated with it called the reference count, if that object is stored in 3 places, like it's a member of a module and it's stored in a list and something else, it'll have a reference count of 3. Every time you drop your reference, like if you remove it from the list, then you decrement the reference count, and so it have a reference count of 2. When the reference count reaches 0, you free the object, because no one's interested in it anymore. So that's when you del, and that's when you reclaim the memory. Python objects use this, and if you have multiple threads that are both trying to access the object at the same time, you could have a race between them trying to update the reference count. You could result in an incorrect reference count, and then you're freeing memory too early, or freeing it too late, and it's a memory leak. We need to address reference counting in order to run Python on multiple cores simultaneously. Globals and static variables, there are a fair number of them. Like specifically, there's a bunch of per thread information that we would need to ensure was kept separate. The different threads are kept separate from each other. And there are a bunch of shared singleton objects, like a string or a module or the small integers. Python pre-creates all the small integers and shares those. And those would, of course, need to work across multiple threads. C extensions run in a world right now. The GIL guarantees that a C extension will only ever run one thread at a time, unless they explicitly say, you know what, threads are okay right now. A C extension has never lived in a world where more than one thread can be running inside it at a time, and they make assumptions about this all the time, and allowing multiple threads to run inside of a C extension is going to break it, so we need to address that. And finally, the atomicity of operations. If you have a Python dict and you add to it, or if you have a Python list and you append to it, there are a bunch of steps that have to happen in order for that to occur, and in Python right now, we just guarantee that no other thread can interrupt you while you're doing those operations. But if we have multiple threads, and a second thread tried to examine that object when you were in one of these incomplete states where you hadn't finished the append to the list, say, it could see the object in an incomplete state. So we need to guarantee that objects don't examine, other threads don't examine objects while they're in these incomplete states. We need to guarantee that those operations are atomic from the perspective of a Python program. But in addition to these 4 technical considerations, I say that there are 3 political considerations. Political, kind of a bad word, but those are the best I could come up with. These are not technical considerations, but these are considerations that are imposed on us by the community or by things that aren't necessarily a technical thing. So the first one, Guido has said, he wrote a blog post in 2007, I'll talk about later, where he said, I would welcome a patch that removed the GIL only if it did not hurt single-threaded code, or it did not hurt multi-threaded code that was I/O bound. That's a very high bar to reach. I say that we also shouldn't break C extensions. We broke every C extension out there with the introduction of Python 3.0, and it's taken us a long time for the C extensions to get ported up to it. If we release a new version of Python, we say, we removed the GIL, you're welcome. Oh, all of your C extensions broke, you're welcome. People are going to get annoyed with us, so let's not do that. Let's not break the C extensions to the degree that we can preserve them. And finally, don't make it too complicated, and of course this is pretty fuzzy. But the idea here is that CPython is very easy to work on. The code is very clear, it's very straightforward, it's very easy to modify, it's very easy to read and understand and reason about. And if we complicate it by adding multi-core support, then that's going to hurt our ability to keep evolving it in the future, to modify it, fix bugs, maintain it, all those things. So let's try to minimize the complexity that we introduce by getting rid of the GIL. So a quick detour, I want to talk about a couple of approaches I don't think will work. People have said for years, if only we could get rid of reference counting and go to, the correct term is tracing garbage collection. This is what everybody else does. Java, C# and the CLR, I think Rust, Go, D, all the modern languages use garbage collection to reclaim objects, to manage object lifetime. It's Python and just a couple others that use reference counting. And conventional wisdom is that garbage collection, tracing garbage collection, is about as fast as reference counting, so that's not going to hurt us. Where it hurts us is it's going to break all the C extensions. This is a major change to the API. All the C extensions work. It's also a more complicated API than reference counting. Reference counting is actually a very simple API, very easy to get right. And even there, we still have C extensions that are getting it wrong. It happens all the time. If we introduce an even more complicated API that C extension authors have to use, we're going to make it harder to write C extensions. We're going to make it harder for them to get it correct, which is really going to add bugs, essentially. So I would say, I don't think we can consider this for now. Maybe it's something we could talk about in the future, but not now. Software transactional memory, this is way cooler. This is the coolest thing. Software transactional memory is amazing. But it's also very early. So if you followed the work at all of Armin Rigo, he's been working on a branch of PyPy for a number of years to add software transactional memory. When he walks in the room, he's the smartest person in the room. He's brilliant, and he's having trouble with it. I think us mortals don't have a chance. So while performance would be amazing in software transactional memory and it would fix all sorts of problems, it would obviously break every C extension out there to a crazy degree because it has an incredibly complicated and hard to get right API. I asked Armin, I was like, could we put CPython on STM? And he was like, you don't want to do it. It's so hard to get right. So I don't think that's approachable. So instead, let's talk about what I proposed with the Gilectomy. And I want to make it clear, by the way, so people say, oh, you're removing the GIL. I'm like, no, I removed the GIL in April. Now I'm working on making it faster. So all of these things have happened, and I have a Python interpreter that doesn't have a GIL that can run some Python programs. Very few. So reference counting, we keep reference counting. Reference counting, that's the API everybody expects, so it's not going to break any code. And it is going to slow down. That's really the problem. I'm using something called atomic Inger and Decker. This is functionality you get free with every Intel processor. This is the ability to add or subtract a number from any integer stored in your computer's RAM in such a way that no other thread can fight you and have a race condition at the same time. It guarantees that this increment or decrement will be atomic. But it costs us a lot. It's 30% slower off the top. I'm going to explore alternate approaches because this is hurting us a great deal with the Gilectomy. Globals and static variables, it turns out this wasn't really a big deal. First of all, the per thread stuff had already, years ago, been moved into this Py thread state variable. I looked and I was like, oh, the work is done. I don't have to do anything here. These shared singletons, that's kind of the whole point of the Gilectomy. Python, everything is public all the time. In order for Python to work, you have to be able to share stuff between threads. So yes, that's part of the package of the Gilectomy. We don't have a problem here. C extension parallelism and reentrancy, there's really no way around it. We're going to break code, and it's kind of the point to change the interpreter, and C extensions are going to break when they first try to run under the Gilectomy. And as far as the atomicity of operations, this is where we replace the one giant lock in Python with millions, and I literally mean millions of locks all over the place, little tiny locks. So there's going to be a new lock API, at least internally. That's what I've done in the Gilectomy. I have macros called pylock and unlock that you use, kind of like PyAnchor and PyDecker. Then the PyType object has sprouted an oblock method. I don't know if it's exposed yet. I expect it to someday be exposed to functions and probably called dunderlock and dunder unlock. Oh, sorry. So what objects need to be locked? Any mutable object. And when I say mutable, I don't actually mean Python mutable, I mean C mutable. So consider, for instance, the stir object. As Python programmers, you're like, oh, well, stirs are immutable. And of course they are. But internally, inside of CPython, there are a bunch of lazily computed fields. Like, for instance, the hash value. We don't know the hash when we start up. It's actually, we store a -1 as the hash value. That's why -1 is an illegal value for hash. So we store a -1, and we look and see, oh, it's -1 right now. We need to compute the hash. If two threads came along and they both saw the -1, they would both compute the hash, and then both of them would override it. And in this case, it's not going to hurt anything. Like two threads wasting a little time and overriding each other's values with the same computed value, that's fine. But there are two other fields, UTF-8 and WSTR, that are internal representations of the string. Those are computed lazily, and those both allocate memory. And so if we had two threads that both computed those and overwrote, we're going to leak memory. That's bad. So we would need some locking here. I don't know if we need a lock per string or some global locks or something, but eventually we're going to need to lock stir objects. I haven't done it right now, so you can't use stirs very much inside of the Gilectomy. Now, what kind of lock do you need? You need what I'm going to call a user space lock. This is not technically, like people said, oh, well, user space lock, that doesn't exist. What I mean here is, this is a lock that only uses user space resources like RAM until there is contention. At the point that you have contention, you're talking about threads and scheduling, you need to involve the kernel. And so you consume some kernel resources while there is contention. Once the contention is gone, those resources should go away and you're back to only consuming RAM. So user space locks are pretty common, actually. Under Linux, we have this wonderful thing called the futex, which is a fast user space lock. It's not actually a lock, it's a lock primitive that you can use to make your own locking. And I'm doing all of my development under 64-bit Linux, so this is what I've been using. Under Windows, there is a long-standing thing called the critical section that I'm assured is user space only until there is contention. And under OS 10, I'm told that the standard pthread library from POSIX, the pthread mutex under OS 10, is a user space only lock until there's contention. So I think we're already good for a lot of the major platforms that we care about. And the other platforms, I don't know what the answers are. Again, it's very early days for the Gilectomy. I'm assuming that they have similar answers here as well. Now, as far as these political constraints I talked about, I say that I can deliver a Gilectomy branch that doesn't hurt single-threaded performance and doesn't break C extensions. Now, you may remember, mere slides ago, I said we made it 30% slower off the top and every C extension breaks. So how can I claim this? The answer is we have two builds. You can build, if we ever merge this, and again, I don't know when it will happen, we should be able to build Python both with the GIL and without the GIL. And the with GIL build would remain the default for probably a very long time. So with the GIL is what the Python we have today, and everything works exactly the same. Your C extensions still work, you still have the GIL, and your code doesn't break, which is great. And then for the crazy futurists, we can compile it without the GIL, and that's when things like locking start happening. So we would have these are all macros in C, which means that we can compile them way into nothing. So pylock and pyonlock in the GIL build would do nothing. And with the without GIL build, they would now do something. So this means that we're complicating the CPython source code by having support for both with the GIL and without the GIL on different lines, and you're gonna have to read the code and understand in different contexts it means different things. Now, in order to keep some sanity in the world, I propose that we also have 2 entry points on shared libraries. So if you compile with the GIL, then you're gonna have the same entry point you have today for a shared library, for a C extension. And in the future, we would have a different named entry point, which means that the without GIL build is strictly opt-in. This means that nobody's code breaks. You have to, as an extension author, you have to say, I'm ready for no GIL. Here's the extension, here's the entry point that you can call that means that you can load me in a no GIL build. This also has the nice feature of you can examine a shared library externally and determine whether or not it supports no GIL builds. It might be possible in the future, again, I haven't explored this yet, but this is just sort of a note to myself. If we took those macros and turned them into C functions, allowed you to call into them, we might be able to make it so that you could write a single .so that supported both kinds of builds. And it would just be like, oh, you call this one when you're no GIL, and you call that one when you're with GIL. And you just have both of them in your code, kind of like we're gonna have in CPython itself. And that would let the extension authors only compile once and not have to face as much complexity and just understand like both. But they wouldn't have to compile it twice and ship 2 different binaries. Now, since effectively this is a new C API, it looks almost exactly like the existing C API, but we have this new locking stuff and some of the semantics are different. Arguably, this is kind of a different C API, and so this might be a good opportunity to say, there are a bunch of things that are recommended practices in Python. These are best practices for C extension authors, but they're not required. And it hurts us because we have to support all this nasty old backwards compatibility behavior. This might be a good opportunity to shed that and say, you know what, now PyType ready, that's no longer optional. This is something, it's possible to create a type in Python and introduce objects into the Python runtime without ever telling Python, hey, I have a new type for you. This is what tells Python, I have a new type for you. We might say, okay, it's required in no-GIL builds. PEP 489 is this thing I don't quite understand, but it's multi-phase C extension initialization. Again, it seems like it's a good idea. It might be a good time to say that's not optional anymore either. Now remember when I said don't make it too complicated? This is kind of where the Gilectomy is falling down a little bit. Now we're gonna have these 2 different builds. We're gonna have code interleaved where this is with GIL and this is without GIL. People have said, we can live with this, Larry, if you can make it fast enough. Now, I have been working on this for a couple of months. My original code name was Confuse-a-Cat. Then I thought of Gilectomy, and I was like, oh no, that's the name. We're done. I've gone back a lot of times to this essay that Guido wrote in 2007 titled, It Isn't Easy to Remove the GIL, on his old Arma blog. And I've reread it, and I keep finding new things that he said. It's really worth reading, and I agree with everything that he says, except the title. Because it turns out, If you know where to start, you can actually remove the GIL in about a week. So here is the list of all the things you need to do in order to remove the GIL. Step 0, switch PyInker and PyDecker to atomic Inker and Decker. That's real easy. Step 1, I should say, decide on what locking mechanism you're going to use. It has to be recursive. It has to be user space only because you're going to have a lot of them. Step 3, you have to add locking to the dict object. You go from top to bottom in the dict object.c. Everything that is an external entry point for anybody calling into it from an exterior module, you have to add locking code. You have to lock at the top and unlock at every exit. Step 3, same thing for the list object. You cannot run a Python interpreter without working dicts and lists because CPython uses those internally as part of the running mechanism of Python all over the place. Step 4, there are 10 free lists that are at global scope inside of CPython, and you have to add locks around all of those, like tuples and I think integers and PyFrame objects. You just need to make sure that anytime someone accesses that free list, you have to lock and unlock. Step 5, you have to totally disable the cyclic GC, the garbage collector, and in particular, there are these track and untrack macros, and you just have to stub those out. Those have to be empty because those are called all the time. I actually originally had locking there, and that was costing me 15% and causing crashes, and I just threw my hands in the air. Step 6, finally, it is time to remove the GIL. You literally can just go and comment it out, and you go and find the macros that are referring to it, and you just make them no ops. You don't have a GIL anymore. You can't run code quite yet because step 7, there's this PyThread state that's storing the state of the running interpreter, and you need to change it. Right now in CPython, that's stored in a global variable, and it's just like, that's the one, that's the thread state right now, and everyone refers to it. And whenever you switch threads, we overwrite that variable with the new thread state. Instead, change it. It's already stored in thread local storage. You just change the macros and the functions so they return the version that's in thread local storage, and that works. And finally, there's just a couple of tests you need to fix. Obviously, all the multi-threaded tests aren't going to work. Most of the single-threaded tests actually still work. There are a couple of tests that assert the size of dict object and list object, and we just changed those by adding the lock to it. So you just need to fix those so that the size is correct, and then those tests will start running. Yeah, people were taking pictures. This is the final version of the slide. I think I'm also uploading the slide, so you can see this later. Now, at the Language Summit, I presented about this, and I said it's 3.5 times slower on wall time, and it's about 25 times slower on CPU time. First, let me tell you those numbers aren't correct. Of course, I don't have correct numbers because the benchmarking is so terrible. But let me explain what these numbers mean. Wall time means if you start the program and watch the clock on the wall, that's how long it took. So that's how long everything took to finish. CPU time, my version is using multiple cores. And so if I'm using 6 cores at the same time, if it takes 3 seconds and I'm using 6 cores, it's used 18 seconds of CPU time, right? So 25x, that's how much time we're actually spending. That's the real CPU time. So just to drive it home, at 25x slower, that means that 4% of the time it's doing your work, and 96% of the time it's doing something else. Now, just to show you what I've been doing, here is Gilectomy's official benchmark. It is a terrible Fibonacci function. Again, I can run very little code inside of the Gilectomy version of Python without it breaking. I can run integers, I can run function calls, I can look things up in dicts, and in particular, this is looking up fib in the module dict over and over and over. You can use strings if you're gentle. There's a lot of stuff that I wouldn't try. So here are benchmarks that I ran on my computer the other night. I actually ran these last night, and on a computer that has 28 cores. So I'm not running out of cores. These are all hardware cores. So the number along the bottom is how many instances. It's fib30. So that's how many fib30s I'm running on separate threads. So I'm running threads in both CPython normal and the Gilectomy branch. The fast one is lower. That's the y-axis is number of seconds. The blue line is standard CPython, and the red line is the Gilectomy. And I want to point out, first of all, the Gilectomy is way slower. Second of all, there's this dip at 4 cores I don't understand. It's just one of these things where probably everything meshed really well, and I got lucky. It was consistent, so I couldn't get rid of it, so I'm just leaving it in the slides. I think the shape of the GIL, the standard Python branch is linear and much faster. And the shape of the Gilectomy version appears like maybe it's sort of curving up. I think it's probably going to keep going up. I don't know. At one thread, you'll notice that the Gilectomy is actually not that much slower. It's only about twice as slow, which is great for me. But again, this is wall time, and I think CPU time is much more telling of the tale. So again, the Gilectomy version is about twice as slow at one thread. At two threads, it jumps to 10x slower. And then it just keeps going up and up. Again, there's this anomaly at 4. When we get to 7 cores, it's actually, I have a slide for this. So again, twice as slow on thread 1 core. This is CPU time for the Gilectomy version divided by the CPU time for the GIL version. So this is effectively the y-axis is now how many x slower. And you can see at 7 cores, I am now 19x slower. That hurts. Why is it so slow? Now, a lot of people, their first guess is, oh, that's going to be lock contention. And the answer is, there is a little bit of lock contention. It's not actually that much. The runtime of my program, let me bring this back, wall time, CPU time. At 7 cores, I used like 90 seconds of CPU time, right? So lock contention, probably like 5 seconds of that. It's not, it's measurable, it's noticeable, but it's not the major thing. It's not costing us 96% of our time. The major thing is really synchronization and cache misses. What's going on here is that we're doing this atomic Inger and Decker. Atomic Inger and Decker, in order to be safe, says, you know what? Everyone's cache, you have to throw away this cache line for this object over here that's storing the reference count. Oh, and we just did it again because we changed the reference count. Oh, we just did it again because we changed the reference count. My test program on 7 threads runs a 500 million reference count changes. And so we have effectively blown away the cache 500 million times. CPython didn't have to bother to do that, so it can do it in whatever it is, 6 seconds. I'm blowing away the cache all the time, so it takes me 90 seconds. That's how important caching is on a modern computer. The real problem here is that nothing is private inside of a Python interpreter. So I'm doing the safe multi-threaded thing at every step in an attempt to make the Python code correct and produce the correct result and not crash. But I have to do everything in the public, safe, multi-threaded way. CPython, of course, doesn't have to bother. It's doing the fast, unsynchronized way because it's assured that only one thread is running at a time. So that's really the challenge. Where we go from here, in general, I and the other people who are volunteering to work on the Gilectomy, what we need to do is change the approach that we're doing. So instead of doing the safe multi-threaded way, instead we modify the code so that we can guarantee that we're only doing this work from a particular thread. And then once we've guaranteed that, we can do it in the unsafe, unsynchronized way that is enormously faster, and we reclaim that speed back. So there are a bunch of techniques that I could talk about. Under reference counting, the next thing I want to try is called buffered reference counting. This is very quickly just the idea that instead of doing the reference count changes immediately, instead you write them down and you send them off to a separate thread, and that thread is the guy who commits all the reference counts. Since it's only one thread doing it, he can do it unsynchronized and he's fine. We could try immortal objects. Immortal objects would be a reference count that never changes, and you just look at that and you say, oh, that's a reference count that never changes, and you don't change it. That means you don't have to change it, which means you don't have any synchronization. You get it for free except for the if statement. Coalesced reference counting, that's where instead of writing reference count changes right away, you just sort of keep a tally. It's like object O, I've added 2 references to it, so it's +2. And then I decrement it. Most of the time in C code, you take a reference to an object, you play with it, and then you drop your reference. So the total delta over time is 0, and so this would throw that away. But the overhead of that is kind of expensive, so I don't know if we would do that. Thread private locking. We're adding thread locks to millions of objects. Most of the time, an object never leaves the thread where it was created. And so if we can, anything that we can do to recognize that and have the object behave in a thread local, like a thread private way, we can save some time. So I have an idea to modify the futex-based lock that I'm writing to make it initially privately locked to the thread, and when a second thread comes along and says, I want to lock that, it'll be promoted to a public lock. But while it's a private lock, we can do the unsynchronized fast operations on it and get the locking effectively for free, because again, it behaves like it's locked to the original thread. Under garbage collection, there's people like Mark Shannon who tells me, oh, there's all sorts of research into concurrent garbage collection, and I absolutely believe him. I don't understand any of that. I think I can take the current garbage collector, the cyclical garbage collector, and beat on it and make it work under the Gilectomy. The idea is that I would force all of the threads to stop. So we'd stop the world garbage collection. And then the track and untrack macros that we're doing that was hurting me before, we would change that into being buffered, kind of like the buffered reference counting above, so that it didn't hurt performance on those individual threads. My final thought for you, that's right, Eric Snow, I think during the Language Summit, suggested, what if we added an automatic lock around C extensions? That would allow a C extension to run in the Gilectomy, and they'd kind of have a little private GIL that would at least guarantee that multiple threads wouldn't be accessing them at the same time. Maybe it'll help, I'm not sure. So my final thought for you is the journey of 1,000 miles begins with a single step. I don't know if the Gilectomy is actually going to work. It's not going to be interesting until the point that adding threads and adding cores makes it go faster rather than slower. That's going to take a while, but we're never going to achieve that until we try, and nobody has tried for 15 years, so I'm trying right now. One last thought, I have enormous quantities. I have these t-shirts, which I'm going to give to people who can sprint on it. You have to know a lot about CPython in order to sprint on it, so you have to be this tall to ride the Gilectomy. But I have enormous quantities of stickers. I don't want to take them home. What am I going to do with all these stickers? So certainly if you, maybe I'll put them on the stage and come to the front and you can grab a couple of stickers. Thank you all, and you tell me if I have time for questions. Oh, thank you. How can I resist? Do we have time for questions? One question.
Only one question.
Only one question. Okay.
He wins.
This is awesome and incredibly clever and super nifty, but wouldn't it be like a lot easier just to use Python for the things it's good at and use Rust or Go or D for the things that they're good at?
You want the conference down the street, my friend.
So the session is closed. Thank you, everybody. And thanks, Larry.